Hey, I guess hope the midterm yesterday was good. We have an odd announcement before the beginning of class that we have been disallowed from playing music at the beginning of the class for copyright reasons because the lectures get recorded and webcast. So we would like to invite people, if you would like to sing or are part of an a cappella group, you can perform from 9:30 to 9:40 if you have a guitar, another instrument. But we unfortunately cannot play music anymore, otherwise they won't let us put the webcast videos up. So we're really sorry, but there's nothing we can do about it.
Well, we can at least boo. We can at least boo YouTube. We can do one boo for YouTube, but I don't know if that's gonna help.
Yeah. Well, anyway, hope you're all doing well after the midterm.
That's the best it can do. Okay, good morning, everyone. I really want to say at the beginning how much I appreciate you all coming this morning after what happened last night. Yeah, the midterm was really late, I think, so thank you for coming. I know it's been hard to wake up in the morning after that effort, but hopefully it will be useful. So what we want to start doing today is already start peeling the onion and looking into how we can leverage the circuit analysis techniques that we learned in the last lecture to try to learn some, let's call them circuit operators, right? So these are going to be blocks or patterns of circuits that will perform certain operations, and you will really only need to analyze them once in your life, right? To understand kind of what that sub-block does. And then hopefully in time, as we build up throughout this course, you'll be able to just use these as Lego blocks, as kind of classes or methods, right, in programming, to be able to capture a certain intent that your circuit needs to do, certain operation, multiply, add, scale by some number, divide, right? All of these invert a signal, things like that. So we're going to learn these, and that will help you not only analyze the circuits faster, meaning not always have to go and write out a full matrix and do the inverse, but will help you to do something that computers cannot do today, and that is to synthesize new types of circuits. Because it's actually really hard for computers to figure out the topology of a circuit from specification. Like if you tell it, do something for me, add 2 numbers plus something else, it's kind of hard for a circuit to go and figure this out, especially if the signals that are involved are not digital signals, not binary, like zeros and ones, very discrete values, but are some kinds of analog signals like we have in the real world. We have essentially some stuff that we're trying to sense, a position or voice, things like that. And that's kind of hard for a circuit, for a computer to process. So we're going to see how to do that, but slowly building this kind of toolbox, right, where we build up one circuit at a time as an operator, and then we figure out how to use it in composition with other circuits. So we're going to do this on a few design examples, and one of them is touchscreen. So you all have seen a touchscreen. You have at least a few in your backpack and your pocket, right? And the ones that you have actually are kind of the latest generations, which we will also look into how those are built later in the course where we learn a new element. But we're going to start with something that was kind of like an older generation touchscreen that can be built with elements that we already learned here. And you can still find these probably in shopping malls. You'll see if you push the screen and it's kind of squishy, then it's kind of this type of screen that we're going to do today. So now you can go and start recognizing where these types of screens are used. Okay, so what I kind of wanted to go, before we dive in, kind of this list of things that we're going to do today, I'm always going to kind of put a little mark here which note you can refer to on the website that follows this lecture. So we had note 11 last time. Note 12 is for this one. And we're going to first kind of review the circuit analysis on a new example, but also we will use that example later very frequently as this first operator in our tool set. Right? So this is going to be a voltage divider example. How do I take some voltage and create a scaled version of that voltage? Right? Where scaled version means less than 1. Right? That's a very frequent operation in kind of analog circuit processing or signal processing, and so that's what we're going to do today. And then we're going to talk a little bit about, if I want to build something, how do I physically construct it? Right? And then there's an important step between physical and electrical quantities. Right? Physical world can have, as we said last time, many different physical quantities involved that we want to measure, but we need to somehow translate them into these very few electrical quantities, circuits, voltages, right? So that our circuits can do stuff. So we have to find a proper way of converting this stuff. And for that, we need to understand a little bit of physics. And I'll go into kind of a 16A physics here, very focused version, that will allow you to do this modeling, right? Once you perform the modeling, you've mapped this physical world into the devices in 16A that we covered already. So these are our circuit elements. We listed those in the last lecture: voltage sources, resistors, open circuits, wires, current sources. That's our circuit element tool set. Once you have these circuit elements and you built a model of that physical world with these circuit elements, you can forget about physics. At that point, you can feed that circuit model to a computer. It will tell you what the result is. You can also apply our 7-step procedure, and you will be able to find the result. You really don't have to worry about physics at that point anymore. But you need to know a little bit to be able to make this translation, meaning from a specification, formulate a model, right? And then, of course, we'll analyze that model to make sure it works. Okay, so let's dive in. Okay, right on. Okay, so let's say we have a circuit like this. Last time we had one resistor. Now I'm going to add another resistor. Okay, so this is going to be R1. This is going to be R2. Just going to make sure we see kind of where the elements end. Okay, so I give you this circuit, what's the first step in a 7-step procedure that we should do to be able to start analyzing this circuit? Put the ground. Yeah, in circuit jargon we call it ground. I prefer kind of a reference node because it reminds you that everything is with respect to that node, right? So I'll just essentially put a 0 here. Right, that's my mark for the reference node. And then remember what we talked about last time, just for people who are confused about wires versus junctions versus nodes, right? Let's say if this element, this R2, has 2 junctions, right? 2 ends of the element, right? This VS also has 2 elements. This here is a wire, right? But note that I've labeled this whole region essentially as a node, simply because that whole wire is equipotential, right? It has the same potential along it. In other words, the voltage between these 2 points is 0, right? That was the definition of the wire as an element. So I can treat that whole wire as one circuit node. And that just simplifies my number of variables that I have to carry. I don't have to carry the potentials on both ends of the wire because I know they're the same value, right? So it just makes my matrix a little bit smaller when I'm solving stuff. So, okay, we're going to say step 1 is label our reference node. And I already did it here, but I'll just redraw it just for the sake of it. Okay, so we're going to say this whole thing is a node, right? And then, what's the next step? Step 2. I've labeled one potential. That potential labeled as 0. What's next? Label the other nodes. Okay, so let's do that. So this will be, let's say, U1, and then I have this one over here as U2. So this is step 3. Oh, sorry, step 2. Label the potentials. Okay? Okay, what's step 3? Someone in the back? After we, yes. Okay, label currents. How should I label the currents? So each element should really have the current. No, the node has some currents coming in it, right? It's a junction. But okay, so let's say each element has a current, right? How should I label it? Should I worry a lot, like in which direction the current flows through the element? No. Who says no? You said no. Why?
Because, like, if you're wrong, you can just put a negative sign on it. It's fine.
Yeah, so let me rephrase that. So the argument was like, if you're wrong, you just get the negative sign, right? This actually comes from as your solution, right? If I put a direction of current that I think it's going through an element, let's pick, for example, here, I'll say I3, right? I3 is my variable, right? I'm solving for it. So I just here determine the direction of this variable. If it later, when I solve the whole thing, it comes out as negative, means, hey, actually, positive current is flowing the other way, right? So that's okay. That actually tells you then how the current's actually flowing through the circuit, that final solution. But labeling a direction doesn't cost you anything. Right? So just go and arbitrarily label the directions. That's completely fine. So we're going to do exactly just that, right? We're going to say this is I1, and let's say over here, this is I2. Right. Okay. So try to clean it up a little bit. Let's do it here. I3, U1. This is U2. Okay, so from here, there is a tricky step. Why do I call this step tricky step? Okay, let me give you about 30 seconds to talk to your neighbors. Figure out what is this step and why is this step a tricky step? Okay. Anyone wants to comment on what is this step and why is it tricky? Yes.
Is it that you have to label the positive and negative elements?
Oh, okay, so let me interpret it. You mean adding plus and minus? Yeah. Okay, so we're doing voltages on elements, right? Yeah. Yes. And why is it tricky? Yes. So, okay, you have to add element voltages. But because we've already added the currents, we now need to be careful so that the orientation of that voltage of the element that we're adding follows the passive sign convention, right? So, what is the passive sign convention? Yes? So the current enters positive or exits the negative part. So let's say here on this one, on this element, let's call it element 3, right? I have I3, and if I'm labeling voltage V element 3, where should the plus go? Up or down? Up, right? So I'm going to say here, this is V element 3, right? And so then I'm going to go and just mark this is V element 1, and then here also this is V element 2. Right. You have to be really careful to always label these appropriately. And the reason is very simple. When we defined the current voltage relationships for each element, remember last lecture, we always use that same convention. So that's why you have to do it here as well. Because otherwise you would lose that connection between the current through the element and the voltage on the element. And you'd get the sign wrong and then everything kind of comes out wrong. Or maybe you do it in one element in the circuit and everything else is fine and you cannot find a bug because there the assignment between current and voltage was not correct, right? So just stick to the same template, everything's going to be fine. Okay, so step 5 is very easy. What's step 5? We need to identify something in the circuit. What we are... Yes? Yeah. So we're going to write what we're solving, right? What is our unknowns. So let's call it here. Step 5, identify unknowns. So let's say our vector x is, we don't know the currents, so that's what we want to find out. And there's two potentials that I don't know in the circuit because the third potential, the third node, I know it's my reference node, right? So I purposely labeled it as my reference node. Okay, so now, step 6, we have to start populating the matrix. So now at this point, you can kind of choose to either use one or the other method to populate the matrix. We need both. We last time, and we normally use KCL as the first kind of set of things. But you could also just use the element IV first. It depends what you like. But let's say we do KCL here. Right. So if we're doing Kirchhoff's current law, we have to identify junctions on which we see how the currents sum together. Right. And we need to identify linearly independent equations. So if I have in this circuit node 1, reference node, and node 2, how many linearly independent equations can I write? I have 3 nodes. Maybe it reminds you of last night, so you're like, wow. Kind of did it last time, but it was actually as simple a circuit as this. It was just all around. So, anyone venture to guess? Yes? 2, right? So the reason is simple. 1 is always redundant because it creates linear dependency. So let's say this first node ties I3 and I1. The second ties I1 and I2. The third ties I3 and I2. So obviously that's a redundant equation because from the first 2 I can figure out the third, right? And that's always the case. So I'm just going to write them. And now, as last time, you can write kind of the sum of the flows going in is equal to the sum of the flows going out. You can also write all of the elements on one side. And then you need to adopt some sort of a convention. For example, convention could be current that flows out of the node is positive, current that flows into the node has negative sign, right? So I'll just write a few. For example, for this node over here, it's really I1 plus I3 equals 0, right? That's our first equation. And I can say that's because, okay, the sum of the currents that come out of the node is I1 plus I3, right? Those are coming out of the node. The sum of the currents that come into the node is 0. There's no current coming into the node, right? So that's the KCL. I can also read this as saying, both currents are coming out of the node, therefore they have positive sign. That's just my convention. Right? Okay. For the next node, that's this one over here, 2, I have one current coming in, one current coming out, right? So that means the current coming in, I1, has to be equal to the current coming out. Now, because I know I'm going to have to put it eventually in the matrix form, sometimes it's just easier to write it immediately the other way, which means I just write it always with a 0 on the right-hand side. So I would actually read this node as saying, I adopted the convention that the exit current is positive. So I'll say minus I1 plus I2 equals 0. Right. Just adopt some convention and stick to it. That's basically the point. And everything will be fine. So that's equation number 2. We have 3 nodes. We found 2 equations. That's fine. That's all we can do. So we can move on. So step 7 is, as we said, element voltages. Right? Okay. So let's take a look at that. Here, there's 2 things we need to do. Right? One is figure out the relationship between the element voltage and the potentials in the circuit. So let's do that first. This purely relies on the definition that what is a voltage? It's a difference of two potentials. Right. So let's take a look here. So let's say for V element 1. V element 1 is here. Right. On one end is U1. That's the potential here. On the other end is U2. That's the potential where my minus sign is. Right. A definition of the voltage, and let's maybe do it here on the side just so people know. If I have potential UA and UB, and I label my voltage here like this, let's call it VC, that is equal to UA minus UB. Right? If I want to really be pedantic, I would actually label this voltage as VAB so that my indices here refer to what is actually my orientation, right? From where to where am I subtracting? So the same thing here. For V element 1, what is this going to be as a function of U1 and U2? Maybe let me give you 30 seconds to talk to your neighbor and try to figure it out. Okay, any takers? What is V element 1 in terms of U1 and U2? Yes? Okay, it's U1 minus U2. Because U1 is at where the plus points to, and U2 is where the minus is, right? So we're measuring from U1 to U2. Okay. What about V element 2? So V element 2 measures between U2 and 0. Yes? Yeah, that's the final answer. But what's in... U2 minus 0. I want to be really careful here because I want you to understand where things are coming from. It's easy once you become a circuit Jedi Knight, to kind of skip all these steps, but then it's actually later hard to go back and explain to someone who knows nothing about circuits where it all came from, right? You need to know the origin of the force to be able to teach the force, right? So that's very important. So if your TAs sometimes skip stuff, remind them that they need to get to the origin of the force. Okay, so let's say VEL3. What is that? V element 3. So V element 3 is between this node, U1, and 0. Don't be shy. Yes? Yes, that's what we want. Okay, so I put a little note here on top saying these equations come from voltage potential definition. It's just a definition that the voltage is the difference of two potentials. So all you need to do is see between which two nodes you have defined this element, voltage, and just write it down. It's very simple. There's no thinking involved, right? Yes? Oh, yeah. So, okay. The question is, how do I know which potentials to subtract? Well, so let's pick V element 2. So V element 2 is this element between potential 2, right? This is this node, and the reference node. So on one end of the element is potential U2, on the other end of the element is potential 0. Oh, what stops me from doing 0 minus 2? Well, the orientation of this element voltage. Plus points to U2. So that means starts from U2, subtract what's on the minus end. Right. Okay. So these are just from the voltage potential definitions, right? So we're going to say, okay, that's one part. The second part is the element IV equations. Okay? Remember from the last lecture, we said, okay, if my element is a resistor, I have some voltage current element equation for that resistor. Well, so I better use it now. Right? Okay, so let's say for element 1, I can express element 1 as what? Current of element 1 and something else. Just a definition of the resistor as an element. R1 times I1, right? That's Ohm's law. That was just a definition of the resistor as an element, right? So I just write that down. And then for the element 2, yes. Okay. And then for V element 3, yeah. So, is it clear why for V element 3 it's Vs? Right? Just for people who are maybe kind of confused a little bit, the plus of V element 3 aligns with the plus of Vs, right? So they're both in the same orientation, right? So that's why if you go back to the definition, how we drew the element voltage versus the internal source voltage, when those matched, you get V element equals Vs, right? Okay, now from these two sets of equations, we can eliminate V element as kind of an intermediate variable, and we can link the potentials to currents, which is what we want. We want to form the matrix that has linear equations, linear combinations of currents and potentials, not voltages, right? So that's why we need both of these. Okay, so let's do that. From the first one, we can write that R1 I1 plus, or I'll have to do it with a minus. So okay, let's do it like this first. R1 I1 equals U1 minus U2, because V element 1 is on both sides. So from here, I will write it in a matrix form. R1 I1 minus U1 plus U2 equals 0. Right. So that's one. The second one is U2 equals R2 I2. So, okay, I can rewrite that as R2 I2 minus U2 equals 0. And the third one is that U1 equals Vs. Right? I don't even have to simplify that. That's already in the form I want. Potential on one side, some constant on the other side. Right? So those are my equations 3, 4, and 5. Remember, 1 and 2 were here. So now I'm just going to go and put all this together in a matrix form. That's all that remains. So let's just do that. So here's my matrix. I have I1, I2, I3, U1, U2. Okay, so let's say the first equation, right? That's this one. You don't see it? Okay. Let's do it like this. The first equation, I1 plus I3 equals 0. What does that imply about the first row of the matrix? Okay, so we have 1, 0, 1, 0, 0 equals 0. Okay, good. The second equation. Anyone? Second row. Yes? 1, 0, 0, 0 equals 0. Okay, great. Okay, let's now move to number 3. Yes? Okay. 0, 0. 1 equals 0. Okay? Oh, sorry. Number 4. Anyone? Yes. 0, negative 1 equals 0. Okay? And the last one? Easy peasy. Come on. Who wants this one? Yes? Okay, great. Okay. I'm not going to have you do GE on this right now, because you did that plenty of that last night. Okay? But it should be really easy, even though it looks scary if it's a 5 by 5. But I'm just going to give you the solutions here, so we can move on to some more interesting stuff. So I1 will be equal to Vs over R1 plus R2. Okay? Who can guess what I2 is going to be equal? Must be some circuit gurus here. Come on. Same thing. That's right. Okay? I3. Almost. Okay, negative. And so this is kind of where a little bit of the reminiscing about what this means can come in if you really want to wonder about like physical meaning of it. If I1 and I2 are the same and positive, of course, that's because there's really one current flowing through this circuit, right? It's just a single loop, right? So normally I1 equals I2. And okay, just because the sign came out positive, that means the current's really flowing that way. But I've labeled I3 the opposite, right? So that's where this negative sign is coming from. Just telling me, hey, your direction is kind of in the opposite direction, right? Yes? I was just goofing. Yeah. In fact, actually, I wanted it opposite so that you can get this negative sign and be confused. Because it really is a key point that you don't be confused if you get negative current in the circuit. It's completely normal. It just means you've assumed a different direction, right? So you don't have to really work hard to figure out where the current's flowing and you label that proper flow, right? That's the wrong thing to do. You're wasting your energy, okay? Okay, so now, what is U1? We kind of knew that even before solving anything, right? That was just Vs. Right? If you look at this thing here, it was just Vs, right? So we really didn't have to just read it off. But U2 is actually not just a rock band, but it's also very interesting as a result here. Okay. So that result, can anyone guess what that result is? I gave you already what I2 is, right? And if you look at the circuit, I2 flows through R2. So if you know I2, you can just apply the element IV relationship to get U2, right? Or the voltage across. In this case, it's U2. So, any idea? Yes. Yes, great. So it was. I'll just rewrite it a little bit differently. R2 over R1 plus R2 times Vs. Right. So Vs over R1 plus R2. That's our I2. Yes. You mean this R? Yeah, I do. That's a great question. Do I want to keep it separate like this, or just do R2 Vs over R1, or R2 times? So I could have written this as R2 times Vs over R1 plus R2. This is because this is really I2. So this is Ohm's law, right? But I'm gonna write it like this because then I can say this is some scaling factor alpha that is less than 1, and that's my operator. That's the coefficient I'm looking for. So if someone tells me build a circuit that scales the input voltage by a factor of 1/3, right, then I know what to do. I'm going to put down this divider, and then I'm going to pick R1 and R2 so that that alpha factor is 1/3. In that case, I'd pick R2 to be a unit and R1 to be twice that, right? And then I get 1/3. Does it make sense? Questions? No, everything's clear. Great. Okay, so this is a key relationship, right? We're going to call this voltage divider. Right. We take a larger voltage, that's our supply. Typically, supply voltage is the largest voltage in the circuit. Everything else is kind of some fraction of that voltage, right? And therefore, in this case, this alpha will be less than 1. Okay. So, we kind of got our operator. So we're going to table it for now, just for a little bit, and then take a look at some of the physical world, what we want to actually build, and then come back to it, to use it as our model. So, okay. I'm going to do... Okay, so I'm just going to draw you kind of like a mechanical contraption how this touchscreen look like, and then we can figure out how to model it. So it's going to consist of a flexible conductor. Okay, so this is this thing in red, and then it's going to have a hard backplane. Which sits behind it. So it's like two sheets. Right? One is squishy, flexible, conducts current. Another one also conducts, but it's very hard. Okay. And let's say the distance here is going to be L. Now what I'm drawing here is really like a one-dimensional touch. Think about like a string that you can touch and it tells you where along the string you've touched. Later we're going to expand into full 2D like a real screen. But we first need to build an intuition and a model and analyze what happens when you have even a single dimension, right? Because that's simpler. Okay. So if I want to touch this, right, I'm going to have my backplane, but the material on top is going to get squishy. Okay, and let's say touches this. Okay? And let's say my finger's here. Right? So I'm like poking it. Okay. And so what I'm looking to measure with this circuit is where along this line I touched it. Right? So this is this L touch. This is an unknown. Right? And what I know is what's the total length of this conductor. Right? So I want to measure L touch over L, meaning some normalized distance on this conductor where I want where to find out where's the location of my finger. Because maybe I'm displaying something there and I'm now pointing to the part of what I'm displaying, so I want to know what is the user interested in seeing, right, or activating, or things like that, right? Now, this is a mechanical quantity. It's distance, right? I need to convert that somehow to current and voltage. That's whenever we do these design tasks, there's a specification. This is a specification. Boss comes in and tells you, I want to measure this mechanical quantity. You go like, oh, I need to figure out a way how to convert that to current and voltage so I can actually go and build a circuit, right? Okay, so need to convert to electrical quantity. Right? So that's our current predicament. We would like to do that, but our circuit elements that we talked about, we kind of removed any physics from that. So we need this link between the physical world and these elements, right? So we're going to do a little bit of what we call 16A physics. Okay? We pledged to you that you can do 16A with zero physics background, right? So that's true. I'm just going to give you a real quick primer in physics in like 5 minutes, and then you'll be able to go off and do these things, right? So, the first thing that's kind of interesting in electrical quantities is kind of what's the fundamental particle or fundamental quantity element of current flows, right? So, anyone knows that already somehow? Yes? Okay, so electron. That's right. That's a particle. It's a negatively charged particle. But just overall, as kind of a more general quantity of the flows, is actually charge, right? So we have charge. Charge can be either positive or negative. And it's a basic element of electrical flow. Right? So let's say, example, electron. Right? Whenever we talk about physical quantities, we also want to know their units. And that's going to be very important when we do the checking of is our math working out correctly. So for this one, Coulomb is a unit, C. Okay. When I put lots of charges together and I flow them through some cross-sectional area for some period of time, I get what? If we put a lot of little droplets somewhere and you run them, you get the flow, right? Or current. That's right. Right, so that's the net amount of charge that passes through some area, let's say cross-section. area over some period of time. So this is important. Right. So let's say we will have the definition that the current is dq over dt. This is the derivative, so like certain amount of charge over some period of time, and we normally do it over a very small period of time, and the amount of charge is whatever is proportional to the current. So the unit for this is coulomb, as we've seen before. The unit for time is seconds, and the unit for current is ampere. A. So now you also see that ampere is actually related to coulomb per second. That's its definition. And whenever you do derivations, you should do this unit check. So always do unit checks. This is really, really important. You'll catch a million bugs this way, and it will exactly tell you actually where you made a mistake. For example, here, if I forgot to divide by time somewhere, I would get that ampere is equal to coulomb. I immediately know I lost the time somewhere along the line. So I'm just going to go back and check, see where it is. Okay? So then we get voltage. We kind of already saw it in kind of a non-physical explanation, right? Voltage was just a difference of two potentials, right? But I didn't really tell you what the potentials are. Right? There was this analogy versus like a mountain height and things like that. But really, a more formal definition of voltage is that it really represents the energy to move a charged particle from point A to point B, or a unit of charge. So it represents the energy to move a positive unit of charge from one point to another, to the other. You can kind of view it as you have a little boulder and you have to kind of push it up the mountain, right? And in doing so, in mechanics, you've expended some work, some energy, right, to overcome the potential energy. This is the same exact thing. You have a charged particle, positive, and you want to move it from this point to this point. Well, you expended some energy. Maybe that energy is positive or negative, depends, right? How the field was opposing this particle, right? But nevertheless, there's some effort involved, and you want to quantify that. So that effort quantification is voltage. How hard was it to move this particle from here to here, right? Okay, so let's say this will be voltage VAB if I'm moving a particle from point B to point A, right? So this is a particle. And the unit for that will be volts. And by this definition, its volts is joule per coulomb. This is energy. Does that make sense? Okay, great. The last element we're going to talk about is going to be resistance, or quantity. We already talked about resistor as an element, right? But resistance as an electrical quantity, we need to understand where does it come from, right? So, real pieces of metal always require a certain amount of energy allow charge to flow through. Right. So what does that mean? Well, think about charge trying to get through the metal. There are atoms in the metal. And this charge, as it's going through, is potentially going to hit an atom. If it hits an atom, it loses energy. Right? So how does it when it exits, it's kind of lost some energy in transitioning from one end of the metal to the other. Right? And that we quantify with, again, what's the amount of charge? What energy was lost? That's the voltage. Right? So going back to our Ohm's law, that's essentially what this definition, what Ohm's law represents. The more charge is flowing, the more energy, the higher the current, right? The more energy is being lost in that same metal. So the voltage is higher. That's why you get this relationship, right? The higher the current, meaning the more charge being pumped in a unit of time through that metal, for that given metal, gives you higher voltage, right? Because more energy is dissipated. Yes? This? This is just point B, point A in particle. Particle, yes. Okay. Yeah, please ask for these things. Sometimes my handwriting gets too small. So the unit for this is volt, amp, times ohm. Okay, so you can take a look at this resistance a little bit more. What we have really is, some conductor which has length L, and let's say some cross-sectional area A. And there's some current I flowing into that cross-sectional area. Right. So we want to try to specify this R. What is the resistance of that conductor? How much will that material resist the flow of electrons, right, or charges? Right. So let's think a little bit about it intuitively. Again, going back to this analogy, what causes the resistance? Like the loss of energy. My charge comes in to the metal, it's hitting the atoms, right, as it's going. When will it have more chance to hit the atoms? When the metal is short or long? Long. The longer the metal is, the more chances, statistically, probabilistically, is for that charge to hit an atom, right? The more it hits, the more energy it loses, right? So the more resistive this metal looks like, right? So if this is a measure of that resistance, should it be proportional or inversely proportional to the length? Proportional, right? So it's L. Now, if I look at the area, if I have more paths to get through some material, is it easier, or do I have a bigger chance of passing by without collision or a smaller chance? Bigger, right? So the resistance is going to then drop with area, because the larger the cross-sectional area is, the less chance I have to get in without actually hitting the atom. Okay. And then I just have some materials property type constant here that just says certain materials have denser atom spacing, so it's kind of harder to get through them. Some others have a little bit sparser, so it's a little bit easier. So this will determine that. Right. Okay. So that's all in terms of physics. So let's go back to our model or our physical wire and try to create a model out of that. Right. So here is what we have in the physical world. We have this piece of wire that bends at a certain location. Right? So I have L touch here. And this other piece is L rest. Right? And I want to create a model out of this. A model means I want to map it to these electrical quantities, like resistance, for example. So how do I do that with these two? I can take this first piece of the wire and make that a resistor, right? So let me do that. So let's say this is R2. And then I have this other piece of wire that's R1. Okay, who can tell me what is R1? I have kind of a model here, right? An equation that helps me relate the physical quantities with an electrical quantity, right? So what would R1 be? Yes? Yep. So it will be rho times L rest over some A. I didn't specify A here, right? Because we're looking at cross-section. Yes? Okay, so the question is, would we specify A? As you'll see in this problem, A and rho don't matter at all. But just to give you an idea, this actually, kind of should look something like this, right? There is always some A involved here, right? But since we're doing like a one-dimensional case, I'm kind of ignoring it a little bit, right? It's just a cross-section. Okay, and what is R2 then? Rho times L touch over A. Okay, so we accomplished a few things. We took a physical thing, we created an electrical model. The electrical model is just these two resistor components. We also were able to relate the physical quantities to our electrical quantities. And from this point on, I don't need physics anymore. I can just go and do my circuit analysis. I first need to build a circuit. This is just a sensor part of it, right? Now I have to build a circuit around it so I'm able to read off the electrical quantities, right? And then I'm done. I just analyzed. So let's say from here we want to build a circuit using this model to measure L touch over L as an electrical quantity. Emphasis on electrical. Right? Now we're in the electrical world. No more mechanics. Right? Okay, so let's see how to do that. Again, I have my R2. I have my R1. And what I'm going to do is I need to at least add something that moves, that creates, it's like a motor force that creates a movement of charges around. So what would that be? A source, right? I need some source of energy, right? So I'm just going to add a voltage source, see what happens. Maybe that's all that's needed. Right? So let's add Vs, right? And let's label even a reference node, right? And I'm going to label the potential. So let's say this is U mid. Right. So, who can tell me right off the bat what U mid is? Without the 7-step procedure. Yes? Sorry, this is R2. Mm-hmm. Yeah. Okay, so this is it. R2, U mid. U mid really means U mid minus 0. Really means the voltage across this R2, right? That is equal to R2 over R1 plus R2 times Vs. Where did you come up with that? How did you... You're like a Jedi, some sort... Okay, so that's the same circuit. This is a voltage divider. Let me see if I can recall that circuit somehow. L2, 2. Aha. Here it is. Okay, so hopefully these two circuits look like a mirror image of one another, right? Vs, R1, R2. We're looking for U mid, right? And U2 was here. Do people pattern match? Is it okay? If you're confused, let me know now, because it's important. People recognize the same circuit? Okay, great. So, of course, it takes a little practice to be able to recognize these things. So if you're kind of struggling, don't worry. In time, you'll be able to see it in different orientations and things like that. So that's completely fine. But it is kind of essential to do that because I really don't want to solve another 7-step procedure on the same exact circuit that I've done it 3 times in a row in previous homeworks, right? And imagine on a midterm or a final. You're in crunch time and you have to do a 7-step procedure and a 5-element matrix inversion and you're like, I really don't want to do this, right? So remember these key operators, right? Okay, but this is not the end of it, right? We just expressed it, we just used an operator, but we really need to go back to what we're looking for, and that's L touch over L. So what happens here next? So let's take a look. I'm just going to replace these values, right? Rho times L touch over A over rho times L touch over A plus rho times L rest over A. I'm just replacing basically these equations, 1 and 2. 1 and 2. Okay, so rhos go away, A's go away. And then I get L touch over L touch plus L rest. And that equals to L touch. Oh, I forgot something. What did I forget? How do I find out whether I forgot that or not? Units, right? So I saw that this is unitless. I'm like, hey, this doesn't make sense. This should be voltage, right? Over L, so times Vs. Vs here. So let's repeat it here. U mid equals L touch over L times Vs. That is actually what I wanted, right? Because my objective was to find some representation of L touch over L in an electrical quantity. Right? And that electrical quantity is this U mid. This is voltage. So, this means I can always measure L touch over L regardless of the material. as long as it's a conductor. Right? It has to be a conductor. If it's not a conductor, the circuit doesn't work. Right? So it has to have some reasonable resistance. Okay. I kind of snuck something by you real quick so you didn't see it. It's like Gollum taking Frodo in these like swamps of Mordor, or however it's called. Like there's this like one path you know how to go to, and there's like stuff around. So let me see if anyone kind of detected that sneaky move. I found L touch over L, but to do that I had to do something, right, in my circuit. What was that? Yes? Mm-hmm. Okay, I have to measure U mid. How do I measure U mid? I just pushed the so, think about it this way. My circuit's supposed to detect where I pushed, right? So, in order to measure U mid, it has to actually know where I pushed, right? But if it knew where I pushed, then why measure? Right? If it knows where I pushed, then it already has the information. Why is it measuring it? Right? Wow. It's a big scam. Right? So, that would be the case if you only had this red squishy conductor, right? If you only had the red conductor, yeah, wherever you put your finger down, of course I have to come with a multimeter, right? Basically say, hey, that's where you are. Okay, so now this resistance is R2 and the other one is R1 and I can do this whole measurement. But I have no idea where you're pressing, right? I would need to do some computer vision to see where your finger actually is, but that's another sensor, right? That's not what we're talking about. So, I need some way of measuring U mid regardless of where you put your finger. That's the trick, right? So, I showed you the element that can help me do that, but I didn't show you how to use it. So, who can maybe recall from the very beginning which other elements that we have in the touch can maybe help us with that? Yes? So flexible conductor is the red thing. That's what we already used. Yes? Yeah, the hard conductor, the backplane. That one also conducts, right? So we're going to use that one, actually. So let me draw you a quick sketch of how that works, and then we'll solve it in the next lecture, right? So physically, so let's say a more realistic model. Okay. I have this squishy material. Okay. And this is where the finger pressed. But now I have this other backplane. And actually, let me just make a connection so it's clear. This is connecting. Right. Now, when I was modeling, right, I said, oh, okay, this length is R2. This length was R1. That was for the red conductor, right? And then for the blue, or for the hard conductor, I can also say, okay, the length here up until the point they touch is essentially, let's say, R3. And then this point is R4. These are all currently unknown to me, because I really don't know where I pressed, right? I want to find that out. So R1, R2, R3, and R4 are unknown. They're unknown. Okay. So let me make a model out of this. Right? So that model has our R2, has our R1. That's what we did previously. Those are the two red ones. Now I'm going to add to this model the other two. Okay? So I'm going to just draw it. R3. R4. And I'm adding this ideal wire here just to basically mark this contact. I could also draw this as a single node. It doesn't really matter. It's the same thing, right? I just want to make it a little bit prettier as a circuit. And that's actually a very important thing. When you see how we draw circuits, you'll often see some wire like this that just makes the circuit look pretty and well organized, but really is a node, right? I could have drawn this as as more of a graph kind of thing. Hey, there's this single node. This is the same model, right? Nothing really changed there. This point is still modeling this particular junction, right? Okay, so now I'm going to add voltage to this circuit model, just like we did previously. So I'm going to have R2, R1, we add VS here. But I now have this other stuff hanging there. Wow. What a mess. Okay. There it is. And this is still my U-mid. See that? Okay. So, I now need to solve this circuit to be able to find U-mid, and hopefully that U-mid now will still be a function of L touch over L. And if that happens, then I'm like, yes. Because I now don't care. I can just measure at a very fixed point at the end of the backplane, hard backplane, and I'll always... I'm giving stuff away. Okay. Maybe I should. So I will be able to measure U-mid by not actually touching the U-mid node. Okay, that's the whole point here, right? So let's call this U1, and let's call it U... I guess we don't need it. I'm just not going to even label it. I'll just add this additional potential U1 here. Okay, so who can tell me what's the relationship of U1 and U-mid in this circuit? Just for the record, this is a really hard problem for you at this stage, so don't feel like... Maybe I give you actually a minute to talk to each other and tell me, like after a minute, what do you think is the relationship of U1 and U-mid? Just use the elements that we've done in the first lecture, right? That's all you need to know. I've introduced one more element here that you know from the last lecture, but I didn't label it. Okay, maybe. Okay, someone want to comment on relationship of U1 and U mid? Any ideas? It's fine if you don't get it right. That's okay. Yes. They are the same. Wow. Okay. Is that a surprise to people? Okay, can you tell me how do you figure that out? Okay, so what is an open circuit? Which piece is open circuit? Okay, so this is an open circuit, right? Right. Okay.
And since there's no current going through an open circuit and voltage across R3 is 0, according to Ohm's law.
Okay, so let me rephrase that just to insert one extra step. This is an open circuit, right? By the definition of the open circuit element, the current going into the open circuit is 0. By KCL, between this element and R3, that also means that the current through R3 is 0. Right? So it means that this current is 0, then this current is 0. Right? And then?
And then use Ohm's law and determine voltage across R3 is 0.
Yeah, so then Ohm's law says if the current through the element is 0, and that element is a resistor, then the voltage across the element is 0. So that means that the voltage between these 2 points is 0. Well, if the voltage is 0 and voltage is a difference in potentials, that means that this thing is also U1. Okay? And now, the last step.
Since it's only a wire between U1 and U mid,
Yes, so then, by definition of a wire, the potentials on two sides of the wire are equal, which means voltage across it is 0, and therefore U1 equals U mid, right? So, wow. Okay, why is this so wow? I'm shocked here. Like, this means I sit at the edge of the hard panel, and I measure the voltage there, and wherever you put your finger, that voltage that comes out tells me exactly where your finger is. That's pretty cool, huh? Okay. People see that? Wherever this U midpoint moves, this U1 will track it. But I'm observing at a fixed point. I don't need to know where your finger is. I'll read it off as voltage. Okay? See you next time. Hey.